On the morning of September 15, 2017, NASA took a wildly successful, multi-billion-dollar machine that had survived 2 decades in the freezing void of space and deliberately steered it into the clouds of Saturn to burn. When the signal finally died and those screens went dark, the team at the Jet Propulsion Laboratory didn't cheer. Many of them cried. For 13 years, Cassini had been their eyes and ears in a corner of the solar system most humans will never see, and now that critical link was gone. The decision to destroy Cassini was driven by a strict scientific protocol known as planetary protection. Space agencies have rigid rules against letting a dormant probe drift uncontrollably, because any microbes that manage to survive the journey from Earth could eventually crash into a nearby moon and ruin the scientific integrity of a future search for native biology. There is a catch to that protocol. You only intentionally destroy a functioning spacecraft to protect a moon if you have gathered enough evidence to believe that moon is actually capable of keeping something alive. By forcing NASA to pull the plug, Cassini's own data proved that our long-held assumption about the outer solar system, the idea that it was entirely sterile and frozen, was completely wrong. To understand how we arrived at that conclusion, you have to look at the machine itself. Cassini was the size of a school bus, packed with a dozen scientific instruments and powered by plutonium. It crossed over 4 billion miles of space and operated flawlessly for 20 years. When it launched in 1997, planetary science operated on a fairly rigid set of assumptions. We spent decades looking for planets that closely mirrored Earth's specific surface conditions, assuming the deep, freezing darkness of the outer solar system was a passive dead zone. The defining legacy of Cassini mission is that it stumbled onto exactly what humanity has been searching for, in a place nobody expected to find it. The data returned from Saturn's orbit dismantled the strict, Earth-centric requirements we had placed on biology. It showed that life doesn't necessarily need a warm, rocky surface or a close, bright star. The disruption started with a moon called Enceladus. It's tiny, only about 313 miles wide, roughly the size of Arizona. Before Cassini arrived, astronomers had assumed it was a geologically inert, completely solid block of ice hanging in the dark. Instead, Cassini flew past a moon that was actively erupting. Massive geysers were blasting jets of water vapor, ice particles, and gas hundreds of kilometers into space, directly from its south pole. The physical laws governing that observation are inescapable. If there is liquid water actively venting into a vacuum, there has to be a substantial internal heat source keeping it from freezing, even though Enceladus receives almost no solar radiation. By flying closer and analyzing those plumes, the science team mapped out the interior. Beneath a thick outer shell of ice, Enceladus hides a global, salty, liquid water ocean. And the salt in that water tells us the ocean is in direct contact with a rocky seafloor. Down there in the dark, the evidence points to active hydrothermal vents. These are identical to the deep-sea vents here on Earth that support thriving ecosystems of microbes far away from the sun. Enceladus possesses the exact confirmed physical environments that are absolutely required for a biological ecosystem to survive entirely in the dark. To test exactly what was happening inside that ocean, mission controllers made a bold choice. They adjusted Cassini's flight path to dive directly through the erupting geysers, allowing its instruments to physically sniff the material. What they detected was extraordinary: high concentrations of molecular hydrogen. In Earth's oceans, hydrogen gas pouring out of vents feeds a metabolic process called methanogenesis. It is a direct chemical energy source used by deep-sea microbes. Layer by layer, the data aligned: water, heat, minerals, and chemical energy. Every single required ingredient for life as we know it was sitting in orbit around Saturn. It wasn't the only world rewriting the rules. Cassini also observed Titan, Saturn's largest moon, mapping a thick atmosphere and complex swirling lakes of liquid methane. It proved that rich organic chemistry thrives, even under completely alien environmental conditions. Saturn's rings offered up a massive surprise. Cassini's final dives revealed the rings are surprisingly young, likely forming between 10 and 100 million years ago. That means a former moon was violently torn apart, rearranging the entire local neighborhood while dinosaurs were walking the Earth. Cassini revealed an outer solar system that functions as a violently active, chemically rich laboratory, one fully capable of producing and sustaining life right now. Just recently, researchers analyzing old plume data identified fresh organic compounds, specifically amino acid precursors. These are the direct chemical building blocks that eventually lead to biology. This creates an incredible scientific frustration. Enceladus doesn't hide its ocean beneath miles of impenetrable ice. It literally launches it into space. Any spacecraft flying nearby can capture and test those samples without ever needing to drill a single hole. The physical evidence is undeniable, yet humanity stopped looking at the exact moment we found exactly what we were searching for. NASA already has a concept ready to go. It's called the Enceladus Orbolander, a spacecraft explicitly designed to fly through those plumes, orbit the moon, and ultimately land on its surface to determine once and for all if it is biologically alive. The blueprints exist, and the science is completely justified. But right now, the mission is stalled, waiting on the political and bureaucratic funding priorities that govern what space agencies are allowed to do. Grounded, building intensity. Cassini gave us the map. It proved that the universe does not reserve the potential for life exclusively for Earth, and it pointed us directly toward an accessible, warm ocean hidden in the dark. Slow, challenging. We have the coordinates. We have the chemistry. Now we have to decide if we are brave enough to go back and find out what is waiting in the dark.